Let me tell you something strange. Right now, as you sit there, reading, scrolling, or just resting, your chair is aging you. Not in the familiar sense of stiff muscles or bad posture. Not metaphorically, not poetically, and not as a clever exaggeration. Physically. Something measurable is happening. Something that would show up on the most precise clocks humanity has ever built. The effect is incredibly small, so small that you will never feel it, never notice it, and never detect it without instruments of extreme precision. But it is real in exactly the same way that gravity is real or motion is real. Your chair is influencing how fast time passes for you. To understand what that means, we have to carefully examine a word we use casually every day: aging. In ordinary life, aging means biological change. Wrinkles form, hair turns gray, cells accumulate damage. It's a slow drift toward disorder. That's the version we experience, the version we talk about. But physics strips away that story and replaces it with something more precise, and in a way more unsettling. In physics, aging simply means the passage of time along your path through the universe, nothing more. If you were to wear a perfectly accurate clock, one that never drifted, never lost a second, that clock would measure your personal time. Not someone else's time, not some universal clock in the sky, but your time. This is sometimes called proper time, but you don't need the term to understand the idea. It's just the time that belongs to you. Now here is where things begin to shift. We tend to assume that time is universal, that it flows the same way for everyone, everywhere. 1 second here is 1 second somewhere else. It feels obvious, almost too obvious to question. But that assumption turns out to be wrong. Two identical clocks, if placed in different situations, can tick at different rates. Not because they are broken, not because they are poorly made, but because reality itself allows time to behave differently depending on circumstances. If one clock is moving very fast, it ticks differently. If one clock is closer to a massive object, it ticks differently. And if you think about it long enough, this leads to an uncomfortable conclusion. There is no single shared timeline that the universe is following. There is no master clock keeping track of everything. Instead, every object, every person, carries its own time. Which brings us back to you sitting in your chair. That chair has mass. It may not feel significant, but it exists, and because it exists, it participates in shaping the physical world around it. It contributes in a small but definite way to the conditions that determine how time passes in your immediate surroundings. You are not just sitting on the chair, you are embedded in a subtle interplay between mass, space, and time. And that interplay is quietly determining how fast, or how slowly, you are aging moment by moment. Not dramatically, not in any way that would change your daily life, but enough to force a realization: time is not something that simply happens to you. It is something that depends on where you are, what you are near, and how you move through the universe. And once you see that clearly, even something as ordinary as sitting down stops being simple. We grow up with a very simple idea of time. A second is a second. A minute is a minute. It doesn't matter where you are or what you're doing. Time just keeps flowing, steady and uniform, like a perfectly reliable river. That idea feels so natural that it rarely gets questioned. You set a clock on your wall, another on your phone, another in a different country, and you expect them all to agree. If they don't, you assume something is wrong with the clocks. But the deeper you look into physics, the more this assumption begins to unravel. Time is not universal, it does not flow at the same rate everywhere, and more importantly, there is no single master clock governing the universe. Instead, every clock, every physical system, measures its own time. And those times can differ depending on the situation. This sounds abstract, but we can make it concrete. Imagine you have two identical clocks, not ordinary clocks, but extremely precise ones, the kind that can measure time differences so small they border on the absurd. You take one of these clocks and leave it on the ground. You take the other and put it on an airplane. The airplane flies around for a while at high speed, then returns. You place the two clocks side by side and compare them. They disagree, not by much, maybe a tiny fraction of a second, but enough to measure, enough to confirm, enough to repeat again and again until there's no doubt left. The moving clock experienced less time. It aged less. Now let's change the situation slightly. Instead of moving one clock quickly, you place one clock at sea level and another on top of a mountain. They sit there, doing nothing dramatic. No high speeds, no complicated motion. And yet, when you compare them later, they also disagree. This time the clock higher up has experienced more time. It aged more. So now we have two effects. Motion can slow down time. Gravity can slow down time. And both of these effects are real, measurable, and unavoidable. This forces us into a new way of thinking. Time is not a background stage where events unfold. It is part of the structure of reality itself, and it responds to conditions, like motion and gravity, in very specific ways. If you move differently, your time changes. If you sit in a different gravitational environment, your time changes. And there's no escaping this by choosing a correct perspective. Both clocks are correct in their own frame. Each one faithfully records the time along its own path. That's the key idea. Time is local. It belongs to the path you take through the universe. Now pause and consider what that really means. At this very moment, your head is slightly farther from the center of the earth than your feet. The difference is small, but it's real. That means time is passing at a slightly different rate at your head compared to your feet. The difference is unimaginably tiny, but it exists. Your body is not experiencing a single, perfectly uniform flow of time. It is stretched across tiny variations, all happening simultaneously. This is not something you feel. Your brain smooths everything out into a continuous experience. You perceive a steady flow, a consistent now. But underneath that perception, reality is more subtle. There is no universal now slicing across the universe. There are only countless individual timelines, each tied to a specific path, a specific position, a specific set of conditions. And once you accept that, the idea that something as ordinary as a chair could influence your aging no longer sounds so strange. It becomes inevitable. Now we can focus on gravity, because this is where the idea becomes both clearer and more unsettling. Gravity is usually introduced as a force. Things fall. Objects attract each other. The earth pulls you downward, and you feel your weight as a result. That description works well for everyday life, and for a long time it was considered complete. But there is a deeper way to understand gravity, one that changes how we think about space and time entirely. Instead of thinking of gravity as a force pulling objects together, you can think of it as a distortion in the structure of space-time itself. Massive objects, like the Earth, the Sun, or even something as small as a chair, alter the geometry around them. They don't just sit in space, they reshape it. And because space and time are not separate things, but part of a single unified structure, when space is distorted, time is affected as well. This leads to a precise and testable statement. The stronger the gravitational field, the slower time passes. This isn't a guess or a philosophical idea. It has been measured repeatedly with atomic clocks of extraordinary precision. If you take one clock and place it at sea level, and another identical clock and place it on a mountain, the clock at the higher altitude will tick slightly faster. It will accumulate more time. Why? Because it is farther from the bulk of Earth's mass. The gravitational influence is slightly weaker there, and so time is less slowed. The difference is tiny, far too small to notice without specialized equipment, but it is consistent, predictable, and confirmed. Now bring this idea closer to your immediate surroundings. You are sitting in a room. Around you are objects, walls, a table, perhaps a bookshelf, and beneath you a chair. Each of these objects has mass. Each of them contributes, in its own small way, to the gravitational environment you are in. The Earth dominates this environment by an overwhelming margin. Its mass is so large that everything else is almost negligible in comparison. But almost negligible is not the same as zero. Your chair still has mass. And because it has mass, it slightly alters the structure of space-time around it. That alteration affects how time passes in its vicinity, including where you are sitting. So, in a very literal sense, the presence of your chair is slowing down your time just a tiny bit more than if the chair were not there. If you could remove the chair without changing anything else, without replacing it with another object, without shifting your position, your local gravitational environment would change ever so slightly, and your clock, your personal passage of time, would change with it. The effect is so small that it borders on absurd. no human sense can detect it. Even most scientific instruments would struggle to isolate it from noise. But the laws of physics do not care about scale in that way. They apply uniformly, from the largest galaxies down to the smallest everyday objects. The same principles that describe the extreme slowing of time near a black hole also describe the almost imperceptible influence of your chair. There is no sharp boundary where the effect begins, only a continuous range from negligible to overwhelming. And that continuity is the important part, because it means that the difference between a chair and something as extreme as a collapsed star is not a difference in kind, but a difference in degree. The physics is the same, only the magnitude changes. And once you accept that, it becomes difficult to look at ordinary objects the same way again. They are no longer passive, inert things. They are active participants in shaping the structure of reality, quietly influencing how space is arranged and how time unfolds, even in the smallest possible ways. Now let's bring all of this into a single concrete picture. Imagine two versions of you. Not metaphorically, treat them as physically real, identical in every way. Same body, same biology, same starting age, and each equipped with a perfectly accurate clock that measures their own personal time. At the beginning, both clocks are synchronized. Now separate them. One version of you remains here, sitting in a chair on Earth, surrounded by walls, objects, and the full gravitational pull of the planet beneath you. The other version is placed far away in deep space, so far that the influence of stars and galaxies becomes extremely small. Not zero, but negligible compared to what you experience on Earth. This second version is not moving quickly. It's just floating, isolated, drifting in a region where gravity is very weak. Now let both versions live. They breathe, think, exist. Their clocks tick forward second by second. From their own perspective, nothing unusual happens. Each one feels normal. Each one experiences a steady passage of time, with no sense that anything is different. That's important. Time never feels distorted from the inside. No matter how it is behaving physically, your experience of it remains smooth and continuous. Now imagine that after a long period, years perhaps, the two versions are brought back together. They place their clocks side by side. And now, finally, a difference appears. The version of you that spent time in deep space has aged more. Their clock shows more elapsed time. They are, in a very literal sense, older. Not metaphorically older, not biologically faster aging due to stress or environment, physically older, because more time has passed along their path through the universe. Meanwhile, the version that remained on Earth, sitting, standing, living under the influence of stronger gravity, has experienced slightly less time. They are younger by comparison. Again, the difference is small. For realistic conditions, it would be tiny, fractions of a second over long periods. But the size of the effect is not the point. The point is that the difference exists at all. Now bring the chair back into focus. The chair is part of the environment of the earthbound version. It contributes, along with everything else, to the gravitational conditions that determine how time flows there. Remove the chair, and you slightly alter those conditions. Add more mass, and you alter them in the opposite direction. Everything around you participates in this process. The walls, the floor, the objects in the room, all of them are quietly shaping the rate at which your time passes. You don't feel this because your entire body, your brain, and every process within you are affected in exactly the same way. There is no internal reference point that tells you something has changed. Your thoughts slow down along with your clock, your heartbeat slows down along with your clock, everything stays in sync from your own perspective. Only when you compare your timeline with a different one that followed a different path through space-time, does the difference reveal itself. And that is the strange, almost paradoxical nature of time in our universe. It is both deeply personal and universally comparable. Each observer carries their own clock, their own measure of duration, but those measures can be laid side by side, and when they are, the universe quietly admits that not all journeys through time are equal. Some paths contain more time, some contain less. And the path you are taking right now, sitting in a chair on a massive planet, is one that ever so slightly gives you less. At this point, there's a natural resistance that begins to surface. Something in your intuition pushes back and says, this cannot be right. Time cannot depend on something as ordinary as where you sit, or whether there is a chair beneath you. A second should be a second. It should not stretch or shrink depending on circumstances. That resistance is not a failure of intelligence, it is a reflection of how the human mind was built. Your intuition about time comes from everyday experience, walking, talking, watching things move, remembering the past. In that domain, time behaves so consistently that it appears absolute. The differences caused by motion and gravity are so small that they are completely invisible to your senses, so your brain simplifies. It constructs a model of the world in which time flows uniformly, the same everywhere, for everyone. That model works extremely well for survival, communication, and ordinary reasoning. It allows you to plan, coordinate, and make sense of cause and effect, but it is still a model. And like all models, it has limits. When you move beyond the scale of daily life, either into very high speeds or very precise measurements, that model begins to break down. The underlying reality reveals itself, and it does not match the simplified picture your intuition relies on. There's another reason this idea feels difficult. Language. We talk about time as if it flows. We say time passes, time moves forward, time slips away. These phrases suggest that time is something like a river, carrying everything along at a steady rate. But that image is misleading. In physics, time does not flow in that sense. There is no external current pushing events from the past into the future. Instead, time is part of a four-dimensional structure, and what we perceive as flow may be tied more to how our brains process information than to how the universe is fundamentally organized. So when we try to describe time using everyday language, we are already at a disadvantage. The words carry assumptions that may not be true. There is also the problem of experience. You never experience different rates of time directly. No matter where you are or how you move, your thoughts proceed normally. Your internal processes remain consistent with one another. There is no sensation that tells you your clock is running slower or faster compared to someone else's. If time slows down for you, everything slows down together. Your heartbeat, your neural activity, your perception. From the inside, nothing changes. This makes the concept deeply counterintuitive. Because it cannot be learned through direct sensation, it has to be inferred through measurement, comparison, and careful reasoning, and even then, it resists becoming intuitive. Finally, there is a deeper psychological issue. Humans tend to look for absolutes, fixed backgrounds against which everything else happens. Space feels like a stage. Time feels like a universal clock. These ideas provide a sense of stability, but modern physics removes that stability. There is no fixed stage. Space can curve, time can stretch, both depend on matter and energy. This doesn't make reality chaotic or arbitrary. It makes it relational. Quantities like time are defined through relationships between observers, objects, and the paths they take. Your chair, in this sense, is not just an object you happen to sit on. It is part of a network of relationships that define your physical experience of time. And the difficulty in accepting that is not because the idea is flawed, but because it asks you to let go of a deeply ingrained assumption that time is the same for everyone. It isn't. And once that assumption is removed, the rest, no matter how strange, follows with quiet consistency.